Hi everybody. It is the last lecture today, which means after tonight we are all done. Hooray. Administrivia for today. I sent out a bunch of messages last night. Make sure that you read them and understand them. They are mostly revolving around like Exam 2 results. Exam 2 went pretty good. The average is like 75. The grades that people will receive, make sure you know what all of the grades mean. I know some students have asked me about a withdrawal grade. You are probably not here watching this lecture if that applies to you, but make sure that you understand what all that means anyway if you're watching this later on the playback. And then finally, all the stuff that you got to know. Make sure that you are studying. I mean, hopefully you aren't going to start studying tomorrow for the exam, because it's going to cover all 10 chapters, 1 through 10, for the exam on Thursday. There are a bunch of things due at the end of the quarter. Chapter 9 quiz, worksheet number 5. And, of course, the deadlines are on the 18th. Really, only the hard deadline is the final. You do have to take the final at some point on the 18th. It will be open all day, just like both exams. I think the syllabus says something different, but I'm going to just change that. I'm going to leave it open for everybody all day. And, yeah. So, between now and then, make sure to ask me any questions about any material or content that you need to go over, because we will be testing you on that very shortly. Last time we left off with this formula, and I showed you how to calculate pH, and also how to calculate H3O+ inside using the 10 to the power of equation. We're going to continue from here. Now, I didn't give you information about when you can use this formula. So far, the assumption has just been use it whenever. And so I gave you a problem that you could specifically use this formula on, so I said it was a strong acid. And it turns out that that only works for strong acids. So we can only use the pH equation for a strong acid because if I have a strong acid, I have the wrong pen here. So here's my strong acid, HA, and I put in water. You'll notice that the arrow that I drew is a forwards-only arrow, which means that 100% of my stuff splits into this, which means that if I know what the concentration of this is at the start, then at the end, I will have the same concentration of H3O+, which I can then put into the pH equation. So that's great. We can do that. But if the acid was a weak acid, let's get a different color here. That's a little hard to see. If the acid was instead a weak acid, then what I have to do is I have a backwards and forward arrow as well. And if I had 1 mole of this, I actually don't know how much of this I end up with because of this double arrow. So I can't use the pH equation for a weak acid without doing some long and complex math, which we're not going to do. I make third quarter engineering chemistry students do this. and it involves algebra, and you have to use the quadratic formula, and it's like, what? Yeah, quadratic formula. Remember this thing? Negative b plus or minus square root b. Remember this? Where you're like, there's no way I'm going to ever use this again. Nope, you totally use it in equilibrium. We're not going to make you do that, so don't worry about it. Suffice it to say, if I give you a strong acid, you can find the pH. If I give you a weak acid, I have to tell you the amount of H3O plus that's in solution. And so I might say something like, a solution has this much H3O plus in it. Tell me its pH. And then you just minus log that number, and you're all set. But I can't give you a molarity of a solution, and then you get the pH from that if it's a weak acid. You just can't do that without doing equilibrium math. Oops. Now, pH is useful, but what happens if you don't know the pH, or you don't know the amount of H3O plus in solution, but instead you knew this? Like, for instance, I gave you a solution of NaOH, and the NaOH is like 1 molar. That doesn't tell you how much H3O plus is in solution, does it? That's where this equation comes in. So if I have OH in my solution, I can instead calculate the POH. It's the same formula. The number that you're going to put in the parentheses right here is the concentration of hydroxide as a molarity. And then it turns out that there's another formula that relates POH and pH together, and that's this. So pH plus POH makes 14. Rearranging the equation, you just take 14 and subtract the POH. So let's do an example with this. Part of this went off the screen earlier. There we go. Okay. I'm not on the right layer. There we go. Okay. So let's suppose that I gave you a... Let's suppose I gave you that solution, 0.0250 moles per liter of sodium hydroxide. What would the pH be? So in order to do this, first we have to figure out the POH, which would be minus log of the amount of hydroxide that's in there. So we know that number is 0.0250 moles per liter. Don't worry about the units when you do log. They'll just go away. And when I punch this in my calculator, I get... Oh, that's not what I get. Hold on. There we go. And then I would put this into the POH-pH equation to figure out what the pH is. And so that would be 14 minus that number I got up there. And that would be the pH. Now that makes sense because a solution that has a lot of base in it should have a very high pH. Remember that acids have low pH. They have some tiny numbers like 1, 2, whatever. And bases have high pH. They should be like 10, 12, 14, whatever. You could do the same thing if I asked you to sulfur OH, where you would turn this expression up here into 10 to the minus POH, is how much hydroxide there is in the container in moles per liter. In fact, I could give you a problem where I gave you the pH and asked you to calculate how much hydroxide there is. So you'd have to turn this number into a pOH, which you could then put up here to get this one. There's all sorts of different problems I could ask you. I'll probably pick one or two easy ones and put them on the final. There you go. That's pretty much all we need to know about pH and pOH. We're going to just use those two formulas. Both this one. Oh, I don't know why it's blue. That's okay. And this one and the pH equation equivalent. Oh, I literally just did this problem, except it was 1 decimal less. So it'll be like 13.4 instead for the answer. But you can check that one to see if it's the same result. So here's my practice problems for you to do. Of particular importance is probably the second one. Blood is very, very pH balanced. Like, you can't change the pH of blood very far away from 7.3. If you do, bad things happen. You go into acidosis or alkalosis. And both of those are very bad. You can die very quickly if your pH gets very far away from 7.3. So that's very important to know if you are in the nursing program, which presumably everybody watching this video is. So you could calculate the amount of hydronium in a sample of blood. The top solution is a weak acid, but I have told you its concentration, so you can find its pH. And then down at the bottom, you can find the pH and the pOH of HCl, which is a strong acid. So do these three problems. We'll go over the answers in a second. Post your answer in the chat when you are ready, and we'll go over them in just a bit. See you soon. just a few more minutes to go over the answers. So please finish the problem you're working on. Alright, let me prepare the screen here. So this first one should be pretty straightforward. I gave you H3O+, and I wanted you to find pH. So we're going to use the formula that gives us pH, which is minus log of H3O+. And the amount of H3O+ that we have in this solution is 5.25 times 10 to the minus 5 moles per liter. So I do minus log 5.25 times 10 to the minus 5. And the number that I get when I hit enter is 4.28. There you go. That's the pH of that solution. Second one is harder because we got to go the other direction. Oops, I didn't mean to move that down. Instead, I give you pH, and we want to find H3O+. So we want to use the other formula, which is that one. So in blood, the amount of H3O+ would be 10 to the negative 7.30. When you punch that in your calculator, you get this number, 5 times 10 to the minus 8 moles per liter. I just put 2 decimal points on there. We don't have to worry about sig figs with logs. And finally, we want to figure out what the pH and the pOH of HCl is. So pH, just like before, we know that the amount of HCl that is in here, HCl is a strong acid, so that means that the molarity that we put in is going to be the amount of H3O+ that's there. So when I do minus log of 14, I get a negative number. Oops. My pen dragged across the counter there. Sorry, minus 1.14. Lost my decimal point there. And then I know that I don't know what I'm writing. Sorry, hold on. I'm writing the wrong formula. I want to write the formula that you have. Technically, what I wrote is correct. But I just want to write the same thing that you have in your notes, which is this formula. But we could rearrange this formula. If I add POH to both sides, then my formula would become this. And I could subtract pH from both sides. And then I would get the formula that I had initially. So since this is what I'm trying to solve for, now I can just plug this number right here. And the POH of this solution would be that. Which is just another way of saying, wow, there's very little hydroxide in this solution. Which makes sense, because it's 14 molar HCl. The way these P scales work is if you have a lot of something, the number that you're going to get will be small. And if you have very little of something, the number that you get will be large. That seems kind of counterintuitive, I know. But that is the scale that we have chosen. And you can actually do P with anything. So it doesn't have to just be H or OH. You could do, like, in water analysis, you could do P calcium or P lead or something like that. All right, that's pH and POH. Let me know if you have any questions. Now, the next thing we're going to talk about before we get on to buffers, which will be the last thing we talk about in this class, actually. Oh, here's the homework practice. If you want to have something to try before the exam, which I highly encourage. Let's talk about why we care about pH. I mean, your body is pretty tightly set around pH 7.3, because that's the pH of your bloodstream. But the stuff around your body has very different pHs, such as acid rain, or maybe you're working with oven cleaner because you're cleaning your oven, which is probably what I'm going to be doing this weekend. Cleaning the kitchen and cleaning the bathroom and all those things that you don't have time to do because you're writing exams. Those things have a different pH than you, and they affect you in various ways. In the solubility lab, we talked about how you can saponify soap with lye, which is a very high pH substance. Acids are very common around you. For example, your teeth and your tooth enamel will dissolve when contacting high concentrations of acids for a long period of time. Obviously, that's not good. So let's look at how this stuff affects us. Here's some numbers that I was able to pull from the internet when I wrote these slides a while ago. The most recent data I could find for the ocean was that ocean water has a pH of about 8 in the year 2000. It's been 20 years since. I would not be surprised to see that that has gone as low as like 7.5 or something like that, because we are acidifying the oceans by adding CO2 to them. Rainwater is about pH 5.5, 5.6. If it does not have any pollution content in it, that's due to carbonic acid from CO2. And if you live in Edmonds, your pH of your water is about 7.5. Now, if you go beyond these ranges, like pH 7 point something, pH 8 point something, pH 6 point something, those are pretty common in the environment. But if you go beyond those extremes, then you start to see rather unusual things occur. The first thing I want to put on the screen is rainwater and how it is affected by atmospheric pollutants such as CO2. There's a lot of CO2 in the atmosphere. You breathe it out. We produce it when we combust fuel, when we burn coal, etc. So there's lots of CO2 out there. When CO2 and water combine, you make this, H2CO3, which is a weak acid. because it's a weak acid, only small amounts of it dissociate. So it only affects the pH a little bit. Pure water should have a pH of 7, but adding an acid to it that's a weak acid slightly lowers it, and lowers it to about 5.5. However, let's suppose that you took the same coal that you burned to make CO2, but the coal had like sulfur in it, because it was a pollutant. Sulfur is kind of everywhere. If you burn that, this happens. Water gets mixed in with SO2. SO2 is the result of burning sulfur. You get sulfur dioxide instead of carbon dioxide. And then the sulfur dioxide goes into the air, and it combines with water, and you get this weak acid. But this is a stronger weak acid than H2CO3. So this is sulfuric acid, which then further reacts with water to make H2SO4, which is a strong acid. And strong acids affect pH a lot. So this is what's known as acid rain. Acid rain forms when you combine water in the air, which there's a lot of, with atmospheric pollutants that contain either sulfur or nitrogen. The nitrogen version makes nitric acid, which is also a strong acid. The end result is that the pH of rainwater in areas with high industrial pollution goes down. And if you've ever been to Pittsburgh, you know what Pittsburgh's famous for, right? 2 things. One, here's where Pittsburgh is, right here. One, it's famous for its steel mills and stuff like that, because Pittsburgh Steelers, right? Their football team is named after it. So it's a very high industrial area. And 2, and I know this because I used to visit there when I was dating somebody who lived in Pittsburgh. His apartment was really, really, really sooty, and it wasn't his fault. It was just that was how air was in Pittsburgh. It was full of soot and ash and stuff like that because of industry. So everything is very dirty. Something else that you might notice if you are in the Northeast and you look at things like statues and stuff. For example, I can't think of a good example, but anything made of limestone, for instance, over on the East Coast will actually slowly deteriorate due to acid rain. Now, over here, we have significantly less pollution because we have less industry, as opposed to the Northeast, which has a lot of industry, by virtue of it just being there longer. The Northeast was kind of where we started when America was colonized, and then we moved this way afterward. So this stuff has just been around for so much longer that it's much denser. But over here in the Pacific Northwest, our rainwater is not very acidic at all, and that's kind of good. So just another thing you can tell your friends when they say, oh, I live on the East Coast and it's better. I'm like, nope, you have acid rain and we don't. West Coast, best coast. And then you can make fun of them for having to go to bed at like 8 p.m. because it's really 11 there. That's what I do anyway. Here's a marble statue. Over time, acid rain will deteriorate marble and limestone because those substances contain calcium carbonate. Calcium carbonate is a base. And we all know what happens when a base... Oops, that's not the right pen. When a base reacts with an acid, you get that, right? That's exactly what happens. The carbonate that's in there becomes carbonic acid, and then the calcium pairs with whatever the pair component would be for the acid, which would probably be a sulfate or a nitrate or something. And you make a salt, and you make water. You also make CO2 in this case. Another thing you have to worry about for acid rain is that acids decompose metals very quickly and cause corrosion. So if you live on the East Coast, your car is more susceptible to corrosion than on the West Coast. Is it a lot? It's noticeable. We have our own issues up here, though. Mostly like just salt in the air. So like salt water accelerates corrosion, too. So it's not perfect. The moral of the story is live in Canada, I guess. I say that because I'm a Canadian, so half Canadian, really. All right, that's pH. Good news about this section, we're not gonna do it because I don't really care about it. It's not super interesting to me, so we're just gonna skip it. And we'll go to the thing that's much more interesting. Buffers. Let's talk about buffers. From a biological standpoint, buffers are incredibly important. For example, if you measured the pH of soda pop, you would find that its pH is like 2. If you pour soda into a beaker of water to see how long it would take it to change its pH, the amount of soda you have to add is on the order of like 1 milliliter. And so that small amount of soda would change your pH, assuming the water was like, say, a replacement for your blood, which it's not, obviously. But if we assumed that the solution in the beaker was your physiology, all it takes is 1 milliliter of soda to push you out of the safe physiological range. And that's absurd. I don't know about you, but when I go and get some soda, I don't drink 1 milliliter at a time and then nearly die from acidosis. That would be terrible. So there must be something in your body that stops that, right? And you might think, well, wait, we have stomach acid, right? Anything that goes into your stomach is going to be extremely acidic. Well, that doesn't solve the problem. That actually makes it worse, it turns out. Because then anything you eat is going to have a pH much higher than when it went in. And then your body has to do something with it. So how does your body prevent all of the acid that's in your stomach? That inevitably some of it can get into your bloodstream because it could be absorbed. How does it prevent your pH from just tanking? And the answer is a buffer. A buffer is any solution that resists the changes of pH. And you are exposed to so many different changes in pH all the time. I mean, especially Diet Crystal Pepsi and Mellow Yellow. Those are, I don't even know it. Nehi Peaches. I don't know. I found this picture somewhere. But these are all soft drink beverages that have very low pH. And if you consumed them, presumably your pH would go down because your body is a solution, right? It's a mixture of solutes and solvents, and the solvent is water. But that must mean that there is something in your body that prevents your pH from going all over the place, because you would just immediately die. If you were curious, oops, well, I mean, that was going to point at what I wanted, but here are the ranges in which a person will die from too low or too high of a pH. And you got to be very careful with pH. But in reality, we don't have to be that careful because of buffers. Buffers will prevent changes in pH, and the way that they do it is the following. I'm going to show you this video later, actually, because I want to just show you what a buffer is, and then we'll show you how it works. A buffer has two things in it. A buffer has some weak acid, and then some conjugate base of that weak acid. You have to have these two things to make a buffer. If you don't have a weak acid, and instead of a strong acid, no buffer can be made. If you have two different conjugates, so like a weak acid and then some other weak base that isn't its conjugate, then they just react and you form a salt. That's not a conjugate. You gotta have a weak acid and its conjugate. So these two things together will form a buffer. Now, the premise behind having a mixture of these two things is that if you expose your buffer, which would be a combination of weak acid and conjugate base, which we'll write like that, If I added hydroxide to my solution, hydroxide won't react with a base. There's nothing there for it to react to. But what it will react is with the weak acid. In other words, for every hydroxide I put in, I neutralize the hydroxide, and I neutralize an equivalent of HA. And what ends up happening is I then turn the HA into its conjugate base. Likewise, if I put H3O plus in here, it will react with the conjugate base to neutralize the acid, which then turns it into HA, the conjugate acid. In other words, I'm turning something that is a strong acid or base, which are these guys. They get reacted, and all I'm left over with are things that are weak. Well, weak things affect pH less than strong things. So if I can neutralize out the strong stuff, just the weak stuff remains, and the pH doesn't change as much. So that's the premise behind a buffer, is we're going to mix two things together, a weak acid and its conjugate weak base, and then we'll examine how each thing works in solution. The intracellular buffer that is used in biology is called the phosphate buffer. And that's what's on the screen right now. So the phosphate buffer is dihydrogen phosphate and monohydrogen phosphate. And so you could see that, oops, I don't know why that did that. You can see that the weak acid, if it reacted with hydroxide, it would eat one of these H's to become water, so this gets neutralized. And in losing an H, it becomes this thing. If we added H plus to it, I would put it right here, and then the solution would become this thing. So if I had small amounts of acid or base, I can neutralize those added acids or bases by using up part of the buffer. And since I already have those things in solution, I'm just turning it into something that's already there. The pH doesn't change very much. Now, how do you make a buffer? There's two ways to do it. The first way to do it is that you just simply put these two things together like we asked for. I could say maybe put this and this. Maybe I have these in the shelf. I'll just throw them into a beaker and add water. But the other way to make a buffer, which we're going to see in this video here. Oops, I didn't erase this. Is that if I take the conjugate base and I add HCl to it, what HCl will do is it will react with this part of the buffer. And so if I ignore this part and this part, we'll come back to those in a second. Then I make its conjugate acid that way. So I'm adding a strong acid to the base to make the conjugate weak acid. Now the other thing that's going to get made is I'm going to make an ACl. But in doing this process, I then generate this and this, which are a buffer. And so what's going to happen in the video is you're going to... I didn't do that. I waggled the pen in a weird direction or something. What you're going to see in the video is that the technician is going to add this substance. I forget which base he uses. It might not actually be this phosphate, but he's going to add HCl to it. And at first, you're going to see that the pH changes like crazy because I don't have a buffer yet. I only have this one. But as I react it with H+, I make both things. And then after a while, once the buffer is created, you can see that he'll be adding HCl to it like crazy, and the pH doesn't change at all. So let's go see the video here. If I could click on it, there we go. Oh, I changed what video I was going to show you. Oh, okay. Well, this is a better one. That's okay. We'll watch this one instead. Oops. We'll watch it if I can get the whole video on the screen here. What was that video? That gamer space. I don't know what that is. That's probably good enough. Okay. So I don't care about audio, but here I have two solutions. On the left here, this solution is unbuffered, and I've added an indicator here to determine its pH. So green represents that its pH is like 7 or 8 or so. If it turns red, its pH is very acidic, and if it turns dark blue, it's very basic. We're going to add HCl to the unbuffered and to the buffered, and we'll see what happens. Alright, so 1 drop. Boop. Alright, what happened to its pH? Holy crap, it went way down to like 2. So that's how much soda would be deadly. It's just a little bit boop of it if your body didn't have a buffer. But if you add 1, 2 drops to this one, you'll see that not much of anything has happened at all because the buffer inside prevents changes in pH. In fact, you have to add quite a bit of this stuff in order to get it to do much. So he's going to just add a bunch to it. So 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. He's adding way more, like 20 drops. And you can see that the pH has barely changed any. He's going to keep trying, though. Drip, 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 drip. And he's barely gotten a yellow, whereas the other one just immediately turned blue. So the next thing to do is add base to it. Or we can add more acid. Yeah, that's fine. Come on, dude. He gets there eventually, I guess. We'll just fast forward. There we go. So we're going to add base to this now. So 1 drop to the unbuffered solution. And you can see it immediately becomes like pH 9. So it jumped up 8 pH units. Now it's pH 7 again. I guess some of it got neutralized. Okay. 1 more drop. Boop. And now it's going to just turn dark blue. So the unbuffered solution does not resist changes in pH. It's very susceptible to them. But the buffered solution, we're going to have to do the same thing again. He's going to have to add tons of hydroxide just to get it back to be pH 7. And he's going to have to add a ton more to get it to be pH 12 to match the one on the right. And the reason for this is because buffers resist changes in pH. Oh, now he's fast forwarding it. Okay. Now in the laboratory, we would have you do this with an indicator. You'd actually do this exact experiment to see how many drops it takes to get to certain colors. And the answer for the solution that isn't buffered is always 1. It takes 1 drop. And the solution, or the answer for the buffered solution, is it takes like hundreds. And there you go. All right, so that's what a buffer is. We're going to take our break now because I have like 20 more minutes of lecture left, and I don't want to do 10, have a 10-minute break, and then do like 2 sentences. So I'll put the title card up here. When we come back, we're going to explore buffers in more detail, and I'm going to show you the equations for them. I don't have the timer up yet. Hold on. That's not what I want. That's what I want. All right, so I'll start the clock. I'll see you in 10 minutes, and when we get back, we will finish off the class. I gotta turn down the music here. And then my cat would like to say something. Huh? Maya? Meow? There you go. Meow? Meow? I hope you can hear her. She says she will miss you. But that just means that at 5 to 7, then I will have to be petting her or something instead of working. So, you know. Meow. Huh, Maya? Huh? Meow? Yeah. All right. So, first thing that I want to do is I want you to look at these pairs of components. And I want you to tell me, is it a buffer? So, for example, if I were to put these two things, that's not what I meant to do. These two things together, would I form a buffer? So, some of them will make buffers and some of them won't. And if you find one that isn't a buffer, tell me why. So, looking at this problem, type your answers in the chat. Like, first one is a buffer, second one is a buffer, third one's not, or whatever. And then we'll go over the answers when we come back. And in the meantime, I will figure out why my cat is still bugging me. See you in a bit. Alright, I'm going to guess that most people are done, because it seems like there's only 5 people watching, and 3 of you gave answers. So let's go over the answers. And I don't actually need to write on that screen. Let's just write on this one. Boop. All right, so we're going to look for conjugates. So first find the weak acid. Here's the weak acid. Its conjugate should be different by just H+. So if I get rid of H+, did I make this thing? I did. So these two are a buffer. But if and only if the acid that I have is a weak acid. And acetic acid is a weak acid, so this one is a buffer. Now, the second one down here will fail that test because it does work here, and so these are conjugates. However, HCl is a strong acid. So because this guy is strong here, this can't be a buffer. And the reason for that is because adding acid to Cl- does nothing. I can't convert this one back into this thing because it's a strong acid. It immediately breaks apart again. Are these two conjugates? They're not. They're not. There isn't even an acid in there. That's 2 bases, so I can't do that. Are these two conjugates? So the first thing that we got to do, whenever you see sodium salts, or any salt really for buffers, you want to split these into their pieces. So this is sodium plus and HCO3-. The sodium part is always useless. You don't ever need to worry about the sodium, so we'll just do that to it. I'm going to split this into its pieces, and again, I'm going to ignore the sodium. And now I can ask the question, are these conjugates? And it turns out they are, because they differ by this H+ right here. So if I get rid of that, then they become conjugates of each other. Or they become the same thing. I hit erase. Darn it. I'll just write what we had. So if I get rid of this H, which would make this 2 here, I would then have the same thing. So these must be conjugates of each other. So which ones were the buffers? They were the first one and the fourth one. And it looks like most people got that, so very good. On the test, I'm going to give you a bunch of components. I'm going to say, here's something, pick the things that will make it a buffer, and you'll have to match the buffers or do something like that. So the last thing we're going to do, the last thing ever, is we're going to watch what happens when you mix your buffer with strong base and strong acid. So this is going to be the chemical reactions for what we saw in that video. So the first thing we're going to do is we're going to add base. I'm going to take hydroxide and add it to our buffer. Now hydroxide is really basic, so the pH should go up a lot, but it doesn't, and here's why. Since this is a base, it's going to react with an acid. The only acid that's available is the weak acid in the buffer, which is this. Now, presumably, I would not be drawing extra lines all over the place, for one. Presumably, we are putting a small amount of this, and we have a large amount of buffer. What that means is that after these react, I will have none of this. It'll all go away. And the amount of this will slightly decrease, and the amount of this will slightly increase. But what I have effectively done is I have turned this thing into this thing. A small amount of it, anyway. And it was already in solution. If I turn hydroxide into something that already is there, the pH changes very, very little. It will only go up ever so slightly. Now, if I do the opposite process by using a strong acid instead, it'll react with the only base that's in the solution. and that would be the weak conjugate base of our buffer. So here's my conjugate base. Here's my H+. It will react with this and get consumed in the process. And I will then turn this into this thing, which is already there. So the pH doesn't go down very much. If the H+ didn't react with the buffer, it would stay in the solution, and it would lower the pH like crazy. But because it gets consumed and it's turned into something else, it doesn't affect the pH as strongly at all. So what do you need to know for how buffers react? You need to know that added strong acids react with the base part of the buffer, and also that added strong base reacts with the acid part of the buffer. And that if you add only small amounts, the buffer stays intact and the pH change is more or less mitigated. Now, is it possible to add so much acid that you ruin the buffer? And the answer is yes. So if I added enough acid to this buffer... I lost my cursor. Hold on, let me just get the pen. So let's suppose that I had that many moles of buffer in there, and I added this many moles of acid. These would then completely neutralize, and there would be nothing of either, and it would all be converted to this. At that point, even adding an extra that much means that the pH would then become that. And the pH would go down very, very quickly after that. So it is possible for you to overflow a buffer. In other words, like if you had a situation where like stomach acid or like intestinal fluid or whatever entered your bloodstream, your pH would change very rapidly, and that'd be very bad. So this is why like getting injuries in like your intestinal tract, like getting punctures or perforations or stuff like that, is incredibly awful, because all of your bloodstream is down there to absorb nutrients and stuff, and you really don't want the pH of your body changing that rapidly. The buffer can keep it in check, but if you suddenly just had like a puncture hole because you perforated your intestinal lining for, I don't know, like I guess like you ate a marble or something, or maybe like a magnet. I've heard horror stories about people eating magnets and then they find each other in the intestines and like bad things happen. That sort of thing could be very, very deadly, because you would overwhelm the buffer that is in your blood naturally. On the screen is the reaction that shows how the buffer components are converted back and forth to each other. And really, remember, because conjugates differ by only H+, and hydroxide will react with H+ to form water, you're just either adding the H+ or you're removing it over and over and over and over and over again. And this process can essentially repeat endlessly as long as you don't overflow the buffer. So your body will do this forever. Now, your body doesn't do this with this buffer in the bloodstream. This is an intracellular stuff, so this is what's in your cells. Your body's buffer is the carbonate buffer. Which is this one that I drawn on the screen. And the way that you make this thing is by combining H2O and then CO2. Well, you make CO2 in your cells. This is a waste product. After you send oxygen and glucose into your cells, and your mitochondria produce ATP out of that, one of the byproducts that you make is carbon dioxide. And so we transport that CO2 back to your lungs, but we don't transport all of it. Some of it we need to keep in the body for a buffer. Now, if you have too much CO2 in your body, what ends up happening is you start to have a pH that's too low. And what your body will try and do is it will try and expel it. And so you start to hyperventilate. This is particularly common when you are exercising. If you are exercising heavily, you produce more CO2 because you're burning more fuel, basically. That CO2 goes into your bloodstream and can overwhelm the buffer. You have too much of that component, and the pH of your blood will go down. So you have to pant. You have to breathe in and out much more quickly to get more oxygen in your body and more CO2 out of your body. The opposite happens if you use up too much of the buffer and you end up over here. If your pH is too high, then what your body tries to do is it tries to get more CO2. And I guess that might be when you hyperventilate. I don't actually know what hyperventilating does in terms of physiology. You've probably seen on like those on sitcoms where it's the old guy who like breathes into a paper bag over and over and over. The primary effect of that is not enough CO2 in the blood. I believe that buffer will appear on the next slide, so we'll talk about that then. We already talked about overwhelming the buffer, but there we go. There's the bicarbonate buffer. So what I want you to try and do, I think this is the last slide. Let me put the homework practice on the bottom. We already answered the second question down here. What I want you to try and do is write the equations for the reaction of the bicarbonate buffer, which is what's in your body, with HCl and sodium hydroxide. And then here's the homework practice. So go ahead and write those equations down to show how those parts of the buffer react with added sodium hydroxide or HCl. And then we'll go over the last answer and then we'll wrap things up. How are we doing? Have we written the equations? I'm going to go over the answers here. For the first one here, if I'm going to react HCl with it, I'm going to need the part of the buffer that is a base. Now, here are my two parts of the buffer here. So we've got the carbonic acid and the bicarbonate buffer. Of these two, this is the base right here. So I'm going to react these two together. And we don't really care about this part because it's pH neutral. But what we have done is we have turned this guy into this guy. So the pH should not go down very much because both of those are present in solution. There they are. If I was going to add sodium hydroxide, remember the sodium's kind of worthless, so we don't care about it. This would react with the acidic part of the buffer, which is this top one. And the result that we would get is we would get the bicarbonate part and water, which is neutral, so we don't really care about it either. But we have turned one component of the buffer into the other. Both of them are present at the start, so the pH doesn't change very much either. All right, there you go. Here's the homework practice again. There is one more thing that you have to do before we finish the class, and that is to celebrate, because we are now done with Chemistry 121. I played my music and it didn't even go through because I didn't unmute the thing. Hold on. Oh, I'm the worst at this. There we go. So now it should play. Hooray! The end! Alright. Thank you all very much for making this a great quarter. Given the circumstances, I realized that this was probably not what you anticipated at the start. But now that you have made it all the way through all of the content, hopefully you can look back at it and say, hooray, I did it. And you did do it. Oops, we're not on a break anymore. Well, we are on a break. We're on a break forever now, because that's it. There's no more lecture. No more material. I have nothing else to share. You will no longer sit down at 5 p.m. to tune into the somber, melancholy voice of your instructor. I don't know where I'm going with this. But I do hope that at some point in the future, when all this is over, all this crazy chaos outside, when you're able to go like to a bar with your friends or get together with your loved ones or just hang out, you look back on this class and say, maybe it wasn't so bad. Thanks again for watching. I will hopefully see some people tomorrow for the Q&A session, the last one. So yeah, you do get to hear me if we have questions. But until then, please make sure to send me some emails. Make sure that you are spending your time wisely preparing for the exam. And best of luck to you wherever you go from here.